Hi, everyone, and welcome to the first fall webinar for the Climate Adaptation Seminar Series. We're so happy to have you here. Today, we're joined by Dr. Michele Barbato, who will be speaking about earthen construction, an ancient solution to the modern problem of sustainable, safe, and affordable housing. Dr. Barbato will be speaking about his research and work on compressed and stabilized earth block construction. So thank you for joining us today. A little bit more about Dr. Barbato. He's a professor in the Department of Civil and Environmental Engineering here at the University of California, Davis. He is also co-director and co-founder of the UC Davis Climate Adaptation Research Center. He received his summa cum laude degree in civil engineering from the Spezia University of Rome in 2002, and his MS and PhD in structural engineering in 2005 and 2007, respectively, at the University of California, San Diego. He's a licensed PE in Louisiana and in Italy. He's an expert in both traditional and innovative construction methodologies and materials, with particular emphasis on new, recycled, and green materials. He is active in the development of performance-based methodologies in earthquake, wind, and hurricane engineering, as well as in multi-hazard applications. Dr. Barbato's research also embraces nonlinear finite element modeling and analysis of structural systems, random vibration theory, structural reliability analysis, multi-hazard assessment and mitigation under current and changing climate conditions, and life cycle cost optimization of resilient and sustainable structures subject to multiple hazards. He is the author of more than 200 technical publications, and we're so happy to have him joining us today. Dr. Barbato, over to you.
Good morning. Thank you very much, everybody, for attending this presentation. I'm Michele Barbato, professor of civil environmental engineering at the University of California, Davis, and also co-director of the UC Davis Climate Adaptation Research Center. And today, I'm very excited to present some of the ongoing work we are doing here at UC Davis on earthen construction. And as you can see, we are going to describe how an ancient solution can be used to solve the modern problem of sustainable, safe, and affordable housing. I will start with a short introduction on what earthen construction is. Describe the advantages and the challenges in using these construction technology. I will then enter more in the details of a specific technology that we are using in our research, that is compressed and stabilized earth block construction. Describe some research that we have done on the feasibility of CSEB houses, and also ongoing research on the use of CSEBs for wildfire resistant building construction. There will be some additional sustainability consideration and then some conclusions. Earthen construction is really a very ancient, the most ancient and sustainable building techniques that has been used by humans to build houses. We have remains of construction made with soil that are more than 10,000 years old. Earthen structures are structures that are built using mainly soil as the base material. There are at least three different technologies of ancient earthen construction. Cob, rammed earth, and adobe. In cob, the mix of soil and fibrous organic material is mixed with water, and then the soil produces walls by being layered to build earthen structures. In rammed earth, the same type of mix is then compacted within forms using rams. And in adobe, bricks are made using the same composition and then by letting the material harden and dry under the sun. And currently, we have still an estimated 30 to 50% of the world population that lives in earth-based dwellings. And we can find the earthen structures all over the world, as shown in this figure, where the orange areas are where remains or existing structures made of earth and soil can be found. So in terms of the motivation of using and recovering these ancient technology, there is a motivation that is really a practical motivation, and then there is a motivation that is more engineeristic and intellectual. In terms of practical motivation, there is a need for affordable and sustainable housing. In the US, we have a shortage of 0.4, almost 500,000 houses per year that need to be built in addition to the one that are already built. We have accumulated a shortage of approximately 5 million houses. According to some calculation, this shortage may be even higher, up to 10 million. We have a shortage of skilled labor in the construction industry. And also we are dependent on construction materials that are coming from other nations or that at least are not local. We have seen what type of disruption in the industry that can create when there is a supply system that is collapsing, like under we had for the COVID pandemic. There are also significant issues related to the energy consumption and the pollution associated with buildings. Most likely, the most important point, it is estimated that we will need worldwide more than 2 billion new houses in the next 8 years. So we need to do something in order to produce this housing, to cover these housing needs, while living in a carbon-constrained future. In particular, this has a highest effect on low-income and disadvantaged populations, who usually are the ones that cannot afford new houses. From an engineering point of view, the interest is really in developing engineered-based design approaches, understanding the different mechanical behavior that earthen construction has when compared with ordinary masonry, understanding and closing the gaps in the limitation of existing numerical models. There is a lack of standardization, and so a lot of work should be directed toward standardizing and codifying the design of these structures. And in general, there is a very limited understanding of the performance and the reliability of earthen constructions. In this presentation, I will focus more on practical aspects that are related more on the practical affordability and sustainability It is also eco-efficient and sustainable in the sense that the embodied energy of earth buildings is significantly smaller than that of other conventional construction techniques. Here you have the comparison of earth blocks with concrete blocks, ceramic blocks, and aerated concrete blocks. You can see there is an order of magnitude of difference in terms of the embodied energy. Also, recent research has demonstrated that earthen construction can reach a good hazard resistance to hurricane, tornadoes, and earthquake loads. And so that increases the possibility of applying this type of structures in different locations where ordinary masonry and ordinary earthen masonry may have been difficult to apply. There are also some challenges that are connected with this type of construction. The first one is that soil is a natural property, is a natural material, thus it is affected by high variability in the properties. You can see here, these are some results from our tests where the variability in the compressive strength of earth blocks is about 5 times larger than the one of concrete blocks. There is also an issue of poor durability against wet climates. This is an accelerated aging test performed by Pacheco, Torgal, and Jalali, where a 20-year aging of this wall was simulated with wetting and drying cycles. You can see at the base of the wall the damage produced by these wetting and drying cycles. Another technical problem is that the material is naturally brittle. Similar to concrete, it is very strong in compression, but whenever there is a tension in the material, you have that the material reaches quickly its peak strength and then it decays the strength very rapidly, which if it is done without too much attention can produce problems, particularly in places where there are lateral loads like earthquake and wind loads. It also, in its typical historical form of mortared masonry, is labor intensive, which has the effect of being particularly costly in places where labor is expensive or available only limited supplies. There are also some less technical and more cultural problems that are connected with earthen construction. One is the lack of engineering-based design codes and standards. These are the latest codes that have been introduced in the US in terms of design of this type of structures. There is the New Mexico Administrative Code, the International Building Code, the International Residential Code. These are all very recent and they are all related to empirical design or prescriptive design, which usually provides designs that are not necessarily the most efficient. And also there is a need for more education among engineers, architects, builders, insurances, lenders, local building officials, and in general, all of the stakeholders that are connected with developing this type of structures and building it in the real world. But probably the most difficult one to fight is the widespread perception that earthen construction is a substantial choice. And this is really connected to the poor performance of earthen structures in other places in the world where the structure have been not engineered and thus have been performing poorly under particularly earthquake loads, but also under hurricane loads. However, this is really a misconception because even if you were using other modern materials, without using engineering principle for their design, they would perform very poorly under the same conditions. So notwithstanding all of these issues, modern and engineered earthen structures have been built and are being built in the world. There are just some examples. There are examples in Europe, Germany, Austria, Switzerland, in Africa, in Asia, in the United States, in New Zealand, in Australia. So it's not true that this material is not being used, but definitely it's not being used with full potential. So going back now to earth block construction, there are three types of earth blocks that are used generally. There is compressed earth blocks, where the soil is compressed mechanically to increase the strength. There are stabilized earth blocks, where the soil is mixed with a chemical stabilizer, generally cement or lime. These also increases strength, but also particularly the durability of the blocks. And then there are compressed and stabilized blocks, which are a combination of the compression from CSEB and the stabilization from the CSEB, which are in which the soil is mixed with the chemical stabilizer and then is also compressed. And these blocks generally can achieve higher strength and better durability than all other blocks. As an example, this is our fabrication of earth blocks that can be built with very different types of shapes. This is a group of our students making blocks using a manual Simba ram that we built in our lab. We have more recently bought an Auram 4000S and an hydraulic machine that allows to mechanize most of the operation that now we are doing manually with our Simba ram. As you can see, that's how the nice block comes out, but with the appropriate molds, we can provide the different shapes that are shown here. And so with this in mind, we started our work by investigating the feasibility of CSEB houses, focusing on the US Gulf Coast, and particularly Louisiana, where there is a very high need for low-income households and affordable housing. There are several challenges there, so that made the research particularly interesting. The quality of the soil is considered generally poor for earthen construction. The climate is hot and wet, and there are high wind loads from hurricanes. And we need to really bring down the cost, because ideally we are trying to provide stable housing for people that are in trailer homes or that cannot really afford anything. We also need to have solutions that are culturally appropriate. We cannot introduce in a location a type of construction that is completely different from what is used there, because that would encounter some resistance in terms of acceptance from the public. And so we investigated the structural feasibility, the architectural feasibility, and the economic feasibility of earthen constructions, trying also to address all of the issues and the challenges that I discussed before. We started with investigating the local soil. This is a soil that was collected around the Louisiana State University campus in Baton Rouge. As you can see, it is mostly outside of the optimal range of composition between silt, clay, and sand for earthen construction. So the need for some stabilization was clear. These are all of the different soils that we have used, with which we started building fabricating our blocks. We investigated the compressive strength, the flexural strength, and all of the different properties with rigorous testing in our lab. We found that in terms of compressive strength, we are able to achieve enough strength already with the 6% cement And then when we investigated the durability and the performance under wet condition, we needed to have a little bit more cement so that at the end our solutions included a 9% and 12% cement. These are relatively high values of cement, and that is really because the soil available locally was not optimal for the type of construction that we were considering. But even under that condition, we could still achieve appropriate compressive strength for our material. Then we wanted to work on our brittleness and the flexural strength. And so we used another locally available material, in particular sugarcane gas fibers, which are a byproduct of the sugarcane production. There are more than 9 million metric tons of fibers that are produced each year in Louisiana and Texas and Florida mainly. This material, about half of it is burned to produce the electricity that is used inside the sugarcane mills. And then the other half of this material is really stockpiled and is actually a fire hazard that needs to be dealt with. So we were eating really two things at once, improving our material and also finding a beneficial use for a waste material. We investigated this performance. I'm not going to describe everything in detail, but by doing flexural tests on the bricks, we found that indeed we could not only increase the strength of the material, but in particular we were improving the ductility of the material, which is critical to ensure safety of the structure. And this is evident both in the flexure test and in the compression test that we performed, where you can see how adding more sugarcane gas fiber has smoothed out the performance of the blocks. We needed to be careful in the amount of fibers that are added to the material because while we are increasing on one side the compressive strength and the ductility, we are also reducing the durability, which we tested with the wetting and drying durability test cycles. We found that there is actually a relationship between the amount of cement and the amount of sugarcane gas fiber that can be used to improve at the same time the durability, to have a proper durability and improve the mechanical properties. The next step was investigating the durability of this material in a weather like the one of southern Louisiana. So what we did was we built a small masonry wall and we tested this wall by just leaving it for 6 months outside in Baton Rouge. Actually, during that period, we had 2 strong tropical storms that passed through the town. So it was actually a pretty severe test for the wall. And in this wall, we protected one side of the wall with a soil cement mortar, a kind of a stucco made with the same mix used for the bricks in order to see how the wall was performing. And as you can see in this time lapse, indeed, the side that was not protected started having issues pretty early on with the rain that is really excavating the mortar, particularly at the top corner. And once the mortar is removed, you can see that the masonry is damaged, the block is damaged and broken. However, on the side that is protected, we didn't find any damage. And even more, when we dismantled the wall, we tested the bricks that were visually intact. And we found that the side that was protected kept increasing the strength because the cement inside the soil continued actually hydrating while they were subjected to the water coming down on the wall. So in terms of durability, we found a way to make this material very durable, even in hot and wet climate like the one of southern Louisiana. We then investigated the strength to hurricane winds. I'm not going to describe these too much in detail, but this figure reports the curves corresponding to different thickness of the walls, so that on the horizontal axis you can read the design wind speed in meters per second at different locations, taken from AC7. On the vertical axis, you have the characteristic strength of the masonry, with the two horizontal lines corresponding to the strengths of the blocks with 9% cement and the blocks with 12% cement. And so when you find the intersection between one of these curves and the vertical line, as long as they are below the level given by the horizontal line, that is an optimal design for that type of structure. And what we found is that we can build walls that can take even Hurricane 5, Category 5 hurricanes in this place that is subject to very strong wind loads. So the next step is finding if this construction is now economically feasible. And we compared the different types of construction, concrete blocks, fired bricks, light frame wood construction, which is obviously the dominant type of construction, which is clear from the fact that it's also the cheapest. We investigated the original mortared earthen construction, and we found that indeed the labor cost for this type of construction, when it is mortared, is quite high, and that is obviously not a point of advantage. But then we developed and we worked on a version that is mortarless with the interlocking blocks, and we were able to reduce the labor enough so that actually this type of construction that is also represented here in the front elevation of a shotgun house to be built in a urban setting, not only is competitive, but is actually slightly cheaper than a light frame wood house, but with a much higher strength and a much better performance under wind loads. Just to explain very briefly what we are doing with these, we are using interlocking blocks with grooves and protruding elements, with also to position reinforcement, with the reinforcement that helps in positioning the different blocks and also in providing additional strength. And with this configuration, we were able to reduce by a factor 2 the amount of labor needed for this construction, as you can see here. And that's all you really need in order to make it cost competitive with the wooden housing. Given that, we started also investigating the performance of this construction for other problems that are typical of California, but really we should say typical of most of the western coast of United States, from California down to southern in Texas, and that's wildfires. Again, on this one, I'll focus mostly on California, but it's a much wider problem than just California. As you can see, in the last years, the damage, losses, and loss of life produced by wildfires has been increasing very steadily. And this increase is really coming, as you can see, there is a very good correlation between damage to structure, loss of life, and losses, even more than the correlation with the estimated acres burned. So what is the reason for that? There are really two reasons. One is that climate change is increasing the wildfire hazard, making things worse and worse. And we are expecting that to actually continue for at least 20 to 30 years before we start having an inversion, assuming we do something about climate change. There is also another problem that is our vulnerability is increasing because we are building more and more in the wild and urban interface, where the problem of wildfire is most severe. And so our risk is really exploding because both hazard and vulnerability are increasing at the same time. Now, in California, we have the California Building Code with the Chapter 7A that is dedicated to the problem of building in the wild and urban interface, because this is a serious problem. I'm not going to enter into all of the details of the fire resistant test standards and the requirements for exterior protection and for defensible space. But fundamentally, what Chapter 7A is doing is trying to build houses that are ignition resistant. That means they are not, once the fire is closed, they are not starting to burn very easily, hoping that the fire will pass over the house without burning it down. And this is because fundamentally there is a widespread understanding that fire-resistant buildings are too expensive to be feasible. And our research is actually trying to go beyond that preconception and demonstrate that we can build fire-resistant building using earthen blocks that are also economically feasible. So we are investigating the performance of earthen blocks here just as an example of what happens, as you can imagine, when you subject wood and earthen blocks to fire. In this case, this is a propane torch at 3400 Fahrenheit. The wood is immediately charred, while our earth block is a little bit of change of color, but nothing much happening. And we are testing these materials in the furnace, and we found that even after 7 hours at 1800 Fahrenheit, which is much more than the requirements for non-combustible material, our blocks are still practically with no damage. We are doing obviously more detailed testing. I don't have yet all of the results ready, so I'm not presenting them. But we are testing the material at different temperatures to see how they respond mechanically at these different temperatures and the effect of fire. Our preliminary results show that actually up to a certain point, the mechanical properties of the material are improving, because what you're getting is fundamentally fired bricks. So they are even stronger than the originally unburned bricks. But we are doing all of these different testing, and we are also investigating how to integrate the other fire hardening systems like roofs, covers, vents, defensible space, so that you really obtain a house that is fire resistant. We are also investigating other sustainability considerations. For example, we have done an investigation on recycling the material used for CSEBs. I'm not going again too much into the details of this, but what we found is that we can reuse the material from damaged bricks to build new bricks that are as good, if not even better than the original bricks. So the material is fully recyclable, which is obviously something very important in terms of sustainability. Another study that is ongoing is the investigation of embodied energy. What we found from the literature is that generally earth block houses and light frame wooden houses have a very similar embodied energy coming from construction. But these studies usually neglect the fact that actually wooden houses burn. And when you include the effect of wooden houses burning from wildfires, actually you get that light frame wooden houses are not very different from concrete block houses, and they are much worse than earth block houses. Also, in terms of operational energy consumption, you can get very significant savings using earthen construction that are between 30 and 70%, depending on the climate. And another advantage that is often not considered is that the design service life of these houses can be much longer than the one of other houses. There are examples of houses that live easily to 100 years, while the current wooden houses have an effective design life, a theoretical design life of 50 years, but an effective design lives of about 35 years. I'd like also to acknowledge some of the initiatives that are ongoing, that are using CSEB constructions for good, for the greater good. The Good Earth Lodge between the Crow tribe and the US Department of Housing and Urban Development to provide housing in the Crow Nation territory. The Brick by Brick program of the Human Services of the City of Scottsdale in Arizona, which is working with the help of voluntary to build houses for people that are homeless. And then the Welcome Home Haiti program in Northern Haiti, where they have developed a farm for earthen blocks, and they're building houses for people that are homeless, or with houses that are similar to the one that you see here. And they are also generating more than 100 jobs for a population that is generally with very low income or with no income. And so these are real world application of CSEB that demonstrate how you can put together affordability, sustainability, and economic and social justice to really help the world population in improving their quality of life. Let me conclude my presentation. We have shown that earthen masonry represent an affordable, safe, and sustainable techniques for construction of houses and also low-rise buildings, even though it wasn't really treated in this presentation. We have identified the issues that are hampering the mainstream use of modern earthen masonry, with some of the solutions that address these issues, so much that we have shown that appropriate feasible solutions are possible for structures that are subject in hurricane hazard in Louisiana. We are also developing affordable fire-resistant construction techniques based on CSEBS for places that are prone to wildfire hazard. And the summary of all of this is that earthen masonry shows really great potential to address climate change and equitable economic development at the same time. Let me really finish with some acknowledgement for the funding agencies and the people that have worked on this research over the years. With this, I'd like to thank you all for your attention, and I'll be very happy to take any question you may have. Thank you.
Wonderful. Thank you so much for a great presentation. We're now going to jump right into a live question and answer session. So we have received some questions already through the Q&A. But go ahead, we invite you to submit your questions using that Q&A button at the bottom of the screen. So Michele, what resources do you recommend when dealing with disinclined, sorry, what resources do you recommend when dealing with disinclined city building officials when proposing a compressed earth block building?
So that's a very good question. Thank you. And is a very pressing one because if we cannot get a permit to build, then all of these work and research is not really very useful. The existing codes are the one that I listed, plus a few other local codes. But right now, the International Building Code and the International Residential Code in their chapter related to adobe construction and cob construction are really the best tools that we have to help local officials understand that this type of construction is not only feasible, but is actually a, something that should be encouraged in particularly in places where there is a low-income population that is rural with difficult to achieve and reach other construction materials, and that is subject to hurricane hazard or wildfire hazard. I don't know if there is a better way to convince local officials. It's really a long process of education that has to involve not only local officials, but also universities, engineers, architects, builders, and everybody that should be involved in using this construction material. So it's a very good question, but there is no solution that is immediately available. But those codes are a very good starting point.
Great, thank you. Another question from Elizabeth Hurtado. She asks, what machine do you use to create the interlocking blocks?
So we have built our own molds for the Simbaram machine that we have built in our lab, and we have been successful in building blocks with protruding elements that can also locate inside the holes for the reinforcement. We just received our Auram 4000 machine from India, and it comes with a collection of molds that allow for different interlocking holes and all of that. We are also planning to still build our own steel molds to try other types of interlocking techniques. But fundamentally, all of the machines can be augmented with molds that are allowing you to give even nice shapes to your blocks. You don't need to have it only in one direction. You can have also interlocking block in multiple directions, and they can have a very pleasant architectural shapes that are giving a very nice feeling also visually to your wall.
Great, and then a follow-up question that just came in from Susan Felderman. How much does an interlocking block press cost?
It depends on what press you are looking at, and you can find some of the prices online. We built our Simbaram ourselves, and we spent about $700 in steel and machining costs. I think that's the lowest price you can get because you are really building it yourself. However, hydraulic machine can go up to 20,000 for semi-automatic machines, up to 60,000 or more for high production level machines that are fully automatized. So it's really depending on what you want to use it for. If you are planning to build your own house on your own, then probably a single ram is sufficient. If you want to build hundreds or thousands of houses, you need some of the bigger machines that can produce up to 500 to 1,000 blocks per hour. But those are quite expensive, so usually you need the company behind.
Great. And another question, Baton Rouge, can you explain why you didn't augment the soil with the traditionally used clay? Or rather, why did you use cement to stabilize and use cement at the same percentage, approximately 10%, as used in concrete, and thus negating any carbon savings?
There are some practical reasons, and there are some simply making things simple. Fundamentally, to perform research, you need to have funding. And if you try to do too many things in any given proposal, you may have actually difficulties to find funding. So for that specific research, we tried to innovate on the interlocking properties of the blocks more than on the material side of the blocks. We are performing at the same time research on using different types of more environmentally friendly materials than cement. Including fly ashes, lime, and other type of stabilizers and processes. But in that specific investigation, we had already our hands full without tinkering too much with the material. So we went with the easy solution. Everybody knows cement, and everybody knows how cement works on soil, instead of doing a in-depth investigation of how to improve the material. But that's a very important direction also of the research, because at the end of the day, you want to have the maximum benefit from a point of sustainability. So you can use amelioration, you can add sand, you can use lime, you can use other materials, and all of that is on the table.
Great. And Marie Richter asked, can you talk about what we would need to build CSEBs on site? I am planning on an earth construction in a remote off-grid location in New Mexico, mountain range outside of Los Alamos.
Fundamentally, you need something to excavate the soil from your property, and some very simple tests that can be done even in loco, or if you are planning to build a larger house, probably you want to have some confirmation from lab tests about plasticity limits and other typical soil properties and soil composition, which will be also useful to identify the need for potentially additional stabilization. And then you need a machine to produce the blocks, a mixer, and fundamentally a lot of goodwill and energy to do it yourself. You will also need a permit, and that may be the most difficult part of the process. However, in New Mexico, the code, I've been showing the New Mexico code of 2015, but that code is actually much older than that. I think this is already the third version. I'm familiar also with the 2009 version, and I believe there was one before that. So you may have a little bit better luck than most in New Mexico, because there is historical records of previous buildings made with earth blocks and with earthen masonry in general. New Mexico uses a lot of adobe, which means that maybe you will have soil that is good even without too much stabilization. Also, the weather is conducive to that. So I guess the luck to find a building official that is familiar with the earthen construction would be the biggest variable in your project.
Great. And then what are the thermal characteristics of the CSEB construction, the R values? Is this viable for cold regions?
So that's a great question. We just submitted a proposal to the National Science Foundation where we are going to investigate that ourselves to have a better understanding of the R values that are given in the literature. In the literature, what you find is that when you look only at the R values, earthen construction appears to be suboptimal and often requires additional insulation. But R values do not account fully for the thermal mass of these buildings, which usually provides an additional layer of defense in terms of the changes in temperature for the indoor environment. So fundamentally, at this point, I would say the literature says that in cold climates, you need to be particularly careful, and often the technical solution is including an additional layer of insulation. However, I've not investigated that directly, and I have some doubt that the need for additional insulation is really a need and not just something that is imposed by the way that the calculations are done in the code.
Great. And Chuck Moffat asked, have you ever experimented with other natural binders such as metacotolin and lime instead of cement? They're currently working on experimenting with natural binders that look very promising, and they hope to eliminate cement from earth building.
So as I said in my previous response, yes, we are investigating other binders. Right now, the only binders we have investigated really is lime and cement. And depending on the initial composition of the soil, there are situations in which lime simply performs better than cement, particularly when the soil, like the one that we used in Baton Rouge, is extremely rich in silt. There is also the possibility of using metakaolin, but we have not estimated that yet. There are several other things that can be used for amelioration. And as I said before, everything is really still to be clarified. There is a lot of information in the literature, but there is not a unified collection of this information that provides all of the benefit and the challenges for these type of problems. Okay.
Sure thing. And then we are coming a little bit close to the end of the webinar here. Michele, would you be able to stick around just a couple of minutes past 11 to answer any questions?
Sure, I can stay beyond 11.
Great. And so we're going to go ahead and continue with the Q&A. John Jordan asked if you could bond the blocks together with a joint that is as strong as the block itself. Would that solve some of the construction problems?
So that's something that we are investigating for our interlocking blocks. We are trying to optimize the shape of the interlocking to see how much shear load we can transfer just using that type of bond without having additional mortar. I think you can divide the question really in two parts. One is how do you reduce the construction issues, or how do you reduce the labor in the construction? And so definitely going mortarless interlocking and using the reinforcement as a way to guide the construction and also add additional strength seems to be the way to go. Another possibility is prefabricated panels and then having a system to connect those panels. It's something that we are investigating, so I cannot respond with a more simple yes or no, but intuitively that would help a lot, and that's what we are trying to get, while at the same time cutting the labor by a factor of 2 in order to be competitive with other construction techniques.
Wonderful. And then Susan Felderman asks, what needs to happen to get these earth block buildings into complete earth building subdivisions and the rental market?
So that's really a lot that has to happen. And there are the issues that are the technical issues, which several research groups are working on. And the technical issues usually can be resolved just by doing the necessary research that has not been done as for other industrial materials that have stronger lobbies and richer lobbies that are pushing for that research. And then there is the cultural changes. There is a lot of inertia in existing industries, in particular in the construction industry. And so the only way to fight that inertia is building prototypes, demonstrating that these houses work well, and then educating engineers that usually study a lot of concrete and steel and a little bit of timber, but may have never seen earthen construction. Educating architects, educating the builders, because another problem you often have is you want to build your earthen house and you don't find anybody that has experience to build it. And then educating the local building officials. If they don't give you the permit, you cannot build. But then you also need to convince insurances and lenders that do not have experience with similar construction and thus are very risk averse. Even if these houses at the end of the day actually are safer than the wooden houses. So the potential is there, but it's not something that will happen overnight. There have been a lot of people working on that for several decades. And now that there is more pressure and we are really living in a carbon constrained environment, there is probably a better initial culture to push for a renewal of this ancient technique that is beneficial under so many different points of views. I don't know if I really responded to your question, but these are really all real world issues that need to be resolved, and they need to be resolved all together.
No, that's a great response. We are going to go a couple of minutes past the hour, but just in case anyone does need to leave right away, I just do want to promote our next webinar for the Climate Adaptation Seminar Series, which is 1 week from today on September 27th with Dr. Naomi Hauser, who will be speaking about climate change and human infectious diseases. You can read more and register on our website, which Sandra just sent in the chat. Thank you. And so we'll go ahead and continue with the Q&A.
And let me also add that all of these presentations, including the extra time, will be posted on our web page probably sometime next week or so.
Yes, great. And so another question from Robert DeJong. Have you had any contact with Texas regarding CSEB code developments?
I have not yet had contact with the code developers, so not really in Texas, but not even here in California. I'm trying to develop as much as possible the technical side before approaching these code developers. However, I've been talking with people that have been working with the ICC for the development of the code in the International Building Code and International Residential Code, also to learn from their experience and be better prepared for when I can actually provide a scientifically valid and defendable position to implement these officially in the code.
Great. And Quentin Wilson asked, how will electrical, plumbing, and communication lines be installed?
This is a very practical question, Quentin. You have been building many more houses that I will ever build in my house. So probably you do know this issue better than I will ever. However, the blocks that we are developing can be shaped in order to include the openings and the space for all of these solutions. In our first trials, we did something with the electrical conduits that was quite successful. And we have never built a full house to clear up all of the possible issues with plumbing. But generally what we did was shaping our bricks so that there were spaces developed exactly for that type of issues.
Great. And Harris Millman asked, what material is used for the beams and columns to add strength to the overall structure?
So it depends, again, on where you are building and for what you are building. For houses, we usually are considering just a bonding beam at the level of the intersection of the walls with the roof, with the different types of solution of the roofs that can be. Right now, we are investigating particularly a non-wooden solution to obtain houses that are fire resistant. And so we have considered vaulted roofs made with the same bricks, or roofs that are made with light framed steel elements. There are also bonding beams that usually are needed in the openings. Often we just do them as reinforced concrete if we are trying to avoid any place of penetration for the fire, but wood would be an appropriate solution also for places where wildfire resistance is not a major concern. In terms of columns, we are not really using columns. The walls are the vertical loading element, and so we don't need columns. It's only where we expect additional tensional elements that we are adding these beams with the materials that are more resistant to tension. But in some places, you may not need really beams that are made of a different material.
Great. And another question from Harris Millman. Have the walls been subject to wind testing to meet high wind zones?
Yes, we have tested the walls to lateral loading in the lab. And both monotonic and cyclic for loads that are representative of very high wind pressures. We have tested the walls both in plane and out of plane, and we have found that the walls can take the loads coming from Hurricane Category 5 and tornadoes EF3 when well designed. In some cases, there is need for additional steel reinforcement. But usually for wind conditions, you can build walls that are resisting even without necessarily the reinforcement. Usually the reinforcement at least our calculations show that the reinforcement becomes necessary when you are in a seismic zone. But for wind conditions, you can actually design walls that are taking those loads without necessarily needing the steel reinforcement. Or in steel, because we went with the easiest solution. But there are also other more natural solutions that can be applied that we have not yet investigated, but that are definitely something that needs to be considered, that other research groups are considering, including bamboo or other materials that are more sustainable than steel rebars.
Great. We're going to go ahead and take just 2 more questions here. So James Halleck asked, for the NM code, the 10-inch minimum thickness is negated by interlocking. Could you talk a little bit more about that?
Can you repeat the question? The 10
Of course. NM code, the 10-inch minimum thickness negated by interlocking?
What do you mean with the, I don't know what it means really negated by interlocking. I think it depends on what you have in mind as the interlocking system. A 10 inches thickness would probably make difficult to have an interlocking element as a protruding element. But there are some other types of interlocking made with grooves that are not necessarily affected by this minimum thickness. But I don't know if I understood correctly the question. So
James went ahead and sent a clarifying question. So New Mexico codes all for 10-inch thickness for bearing walls. Does the CSEB overcome that?
In the sense that you can make walls that are less thick than that? Am I interpreting that correctly? Maybe I can respond to this question after additional clarification offline and post that solution to the person that is asking it so that I understand better the question. I don't want to just guess. Right now I'm kind of guessing.
Sure thing, not a problem. And then Mark Chalong asked, what percentage of a finished homes do you consider for walls, materials, and labor?
So the way that we evaluated our cost for the example that I represented was by using the construction cost data for the different components. And so it wasn't presented as a percentage cost of overall house. I don't remember what was the cost. I believe it was about $40,000 out of it, 120,000 house. So it was close to, it was 25 to 30%. But the way that we did it was evaluating really the cost of element by element using the posted and available costs in the literature. We used the data from RS means and we included the material cost, labor cost that included both procuring the material, preparing the bricks, and putting the bricks in place. And then we had also the typical overhead for a construction company to build the different parts.
Great. And then our final question for the webinar, Harris Millman asked, what material is used to support the earth block roof that is non-flammable in lieu of trusses and plywood decking?
So as I introduced in a previous question, we are investigating different types of solutions. One solution that is the one that is readily available is using light formed, cold formed light frame steel elements that are not flammable. And then we are also considering the construction of more traditional roofs that are made of material similar to the one on the walls. These are usually a vaulted or dome type of roofs where the strength comes from the geometry, so that the load is mainly transferred through compression instead of tension. If you want to have a straight type of roof like the one that are commonly seen in houses, you do need lintels and beams. In order to avoid wood, we found that probably the cheapest solution that is readily available is cold formed steel.
Great. Thank you so much, Dr. Barbato, for, again, a wonderful presentation. And thank you for the audience for those great and engaging questions, and for sticking around about 15 minutes past the hour with us. Dr. Barbato will be available via email if you have any additional questions. And again, I just do want to promote our next Climate Adaptation Seminar Series webinar in 1 week with Dr. Naomi Hauser on climate change and human infectious diseases. Michele, do you have anything else you wanted to say before we wrap up? I just wanted to thank everybody for being here. I was very happy to see the interest that this presentation has attracted. I really look forward to opportunities for discussion and collaboration with a lot of the folks that I've seen in our question and answer in the chat. Some of them already know me. Some of them, I already know them for their great work in Earthen Construction. And this is very exciting. And I'm really convinced from an engineering point of view that this is a very good time to push for Earthen Construction as a sustainable alternative to the type of construction that we are using right now, with so many beneficial aspects that sooner or later everybody will realize this is a viable alternative and not just a type of construction that can be used only in very rare situations. So I'm very excited, and I thank everybody for being here. And I invite everybody to follow also on our future climate adaptation seminar series. Hopefully we'll be able to continue that beyond the fall quarter with our climate adaptation research center that we just started here at UC Davis. Looking forward to working with other people that have similar interests and similar will to change the world for the good. Great, very well said. Well, thank you so much, everyone, for attending, and I hope you all have a wonderful Monday. Thank you.